video game science and UFOs. What is a video game programmer doing analyzing UFO videos? What am I doing? Well, I am portrayed as a UFO expert video analyst, and I'm portrayed this way quite often. You may have seen me on TV, and you sometimes, I'm giving my analysis of a UFO video, or sometimes I'm just giving my opinion about the current state of UFO affairs. But the media apparently thinks I'm an expert. So how exactly did I get into this position? Let's kind of go back in time, and I shall explain. How it began. My first computer was a ZX81, and I was a nerdy kid, and I've been programming video games ever since. I got my ZX81, which of course came out in 1981. I then graduated the next year to a ZX Spectrum. These are British computers, of course, which is why they're the ZX Spectrum. And then I graduated to an even bigger computer, the Atari ST, which had 1/2 of a megabyte of memory, and a Commodore Amiga, which had about the same. I went to college, but eventually I had, unfortunately, to get a job. So I joined a computer games company. And this was the first commercial game that I ever worked on. It was called Tony Hawk's World Snooker back in 1989, which is 34 years ago, I think, a long time ago. This game is a very two-dimensional game, very 2D. It's just this simple overhead view of very kind of blocky pixel graphics. Really was kind of a fun game at the time. Next game I did was called Rotox. Rotox was a weird overhead rotating shooting game, hence the name Rotox. It used quite a bit of math and geometry to do this rotation. I mean, it wasn't particularly complicated, but it taxed my limited skills at the time. It's mixed polygons with pixel art, so it was kind of a novel thing for the time. And the company I was working at when I made this went bankrupt during the middle of the development, so it was a memorable time. After that, I did some conversions of arcade games. This is a very two-dimensional game, just a side-scrolling shoot-'em-up called UN Squadron, where the United Nations goes into African countries and kills lots of people for some reason. Fun times. After that, I co-founded my own company called Neversoft. And the very first game we did was this one here called Skeleton Warriors. Now, Skeleton Warriors was a bit of departure, and it was a little bit more three-dimensional. You can see the kind of background on the ground there moves around in 3D. And the characters were actually 3D models that were rendered out in 2 dimensions. So it was the evolution of video games. The next step in that evolution was a game called MDK. Which was the first game I did, which was fully 3-dimensional. You see, we have a large 3D world, pretty empty because you didn't have very much memory back then, 3D aliens and 3D ships. So I'm gradually moving from 2 dimensions to 3 dimensions, which will become important later on. Then we did a game for Activision, a big company in Santa Monica, and this was a game called Apocalypse, which stars a character based on Bruce Willis, who at this point is running around a version of the White House, possessed by demons and surrounded by a pit of lava. Typical type of thing you'll find in a video game. And then last, but decidedly not least, I did a game called Tony Hawk's Pro Skater, which this is, Tony Hawk's 4, I believe, but there were 4 versions of it, 5 versions of it that I worked on. I was the technical director at the time at Neversoft Entertainment, and I did a lot of the programming, I did a lot of the physics, and I did a lot of the debugging because there were a lot of bugs in it. Tony Hawk's Pro Skater contains quite a bit of physics. It's not always the most realistic physics. The gravity, for example, is somewhat reduced to the gravity we're used to, so we can get a much better hang time. And the main character is somewhat unencumbered by the hindrances of momentum. So he's able to change direction very, very rapidly, which makes for a fun game, but takes some liberties with physics. So after programming video games for a while, I kind of slid out of the video game industry in the kind of mid to late 2000s, and I transitioned to becoming a writer. The first writing I did was actually technical articles for Game Developer magazine, because all I knew at the time was game development. So write about what you know. This was an article on practical fluid dynamics, which is a very mathematics heavy and very coding heavy way of simulating stuff like smoke and water for use in video games. But then I moved on to other things that interested me, and I was very interested in skepticism and investigating strange claims and things like chemtrails and whatnot. And I started doing more skeptical writing. I started Metabunk, which you heard about earlier. I wrote a book, Escaping the Rabbit Hole, about conspiracy theories. And I write a column for Skeptical Inquirer. And I've looked at all kinds of different conspiracy theories, chemtrails, 9/11 conspiracy theories, flat Earth, election fraud more recently, and like coronavirus related conspiracy theories, and a bunch of other like conspiracies, pseudoscience, quackery, and things like that. And during the course of that time, I have been gravitating slowly towards UFOs. And so because UFOs has become my kind of main thing that I've been investigating recently, I get portrayed as an expert. And here's me being portrayed as an expert on Brian Dunning's upcoming documentary, which is called The UFO Movie They Don't Want You to See, which is looking very nice. It does a good job of showing the various videos I've been investigating and the debunking in a relatively technical way. But yeah, I show up on things like this a lot. I show up on TV, I show up in documentaries, I have a YouTube channel, and people see Mick West being portrayed as an expert, and they get a bit upset about it because they know I'm not an expert. I'm just a video game programmer. And the people who get most upset about this are the people on Twitter. For example, here's a tweet from a couple of years ago. Mick West is no expert. He is a video game programmer. He likes to debunk by selecting straw-man arguments like speed and rotation. So yeah, I'm a video game programmer. I'm no expert. So according to at Shalanzar, this means that all of my arguments should be discounted. Here's another one. Someone says, I'm glad you're interested in the science, but Mick West is a video game programmer. He's not a scientist. I suggest you reach out to professional scientists who have studied these incidents. So again, I'm just a video game programmer. I'm not a scientist. And more specifically, this comes up into play when I'm kind of pitted against somebody else. Like, for example, here, this person here, Cloud Jimmy, is comparing me against one of his favorite scientists, who's a UFO scientist. And he says, this guy has a BS in electrical engineering, a master's in physics, a PhD in optical science, a master's in astronomy, a PhD in aerospace systems engineering, versus Mick West, who is just a video game programmer. Stop being a clown, Mick. I hadn't actually noticed that one before. But yes, apparently I'm just playing a expert on Twitter and on YouTube, and you should ignore what I say and listen to this other guy because he has more credentials than me. Now, we're all good skeptics here. This is the Center for Inquiry. And so you might recognize this as being the argument from authority fallacy. Can we say something is true just because an expert says it is true? Well, we know that's a fallacy. So yes, that is in fact a real thing. But really the broader issue here is one of science communication. It doesn't really matter if they pick one expert or the other, because the person themselves doesn't actually understand the science. So using the argument from authority becomes the only thing that they can fall back on. If we can't communicate what the science actually is, then the person has no choice but to pick an expert. And of course, they're going to pick an expert who they prefer. And if all things being equal, they're going to pick an expert who has more credentials. So, of course, they're going to pick the guy who has multiple PhDs, and they're not going to pick me, who's just a video game programmer. So the issue really isn't that it's a fallacy. The issue really is about communication, that we need to do a better job at communication. People don't understand all the science, so they pick the expert they prefer. Ultimately, it should be about the investigation. I'm just a games programmer, but if I can do a good investigation based on my game programming skills, that's going to go a long way. So what does make a game coder, a game programmer like myself, a good UFO investigator? Well, let's do a brief list of things that game coders typically understand and are good at. Pixels, the very elements that make up make up an image on screen or a video. the little square things that you see when you zoom in. Surprisingly, a lot of people don't really understand exactly how they work. Things like the resolution of the image, what happens when you rescale it, when you resample it, when you make something bigger or smaller, and things like the colors, like how many different colors you can have. This is called the color depth. How many colors can you have in a pixel, and what happens when you do various things with it? There's 3D math. Of course, when you do 3D video games, 3D math is very, very important. There are these technical things, vectors, which is just a three-dimensional position, transforms, which is a way of moving one position into another position or rotating things and things like that, and perspective, which you all understand. Small things that are far away look smaller, and you have to code that essentially into your graphics. There's 3D physics. When I was doing Tony Hawk's Pro Skater, the physics of the skater skating over the surface and going up ramps and long rails and things is three-dimensional physics. It's very simple, but it uses Newton's equations of motion, and it's typically all you need in terms of physics knowledge to be able to analyze the motion of something in 3D. There's a thing called data munging, which sounds fun, but all data munging is taking data from one format and turning it into another format. Like you've got a JPEG and you want to turn it into a GIF or something like, or a PNG, or you got one set of 3D coordinates and you want to turn it into a version that some software can use. Something you get very good at as a video game programmer is taking data and converting it into other data so it can be used for something else. Human factors. Yeah, this is something you might not think of as a video game programmer, but I'm programming a game and people are going to be playing that game. And so I have to understand the human factors of how they interact with what I do and how I can change my programming. For example, like what happens when you press a button, or what happens when you hold a button down, or you lean the sticks left or right. How do people perceive that? And how do I program it so that they have the best experience? And how do I get over any little hiccups that they might have? There's things that you might be familiar with, like compression, when you take an image and you make it smaller. Video compression, when you take a video or something, you might see little artifacts and little flickering things. These are things that you deal with a lot in video game programming, because we typically use video and we don't have very much memory, especially back in the day. So we use a lot of compression. So I'm used to the way things look with certain types of compression, which is very good for spotting issues to do with compression. Things like frame rate, just it's a standard video game thing. Back when I was a kid, we made our videos at 30 frames per second, and then we would make them at 60 frames per second when things got more powerful, and now they're kind of variable. PCs go like 120 frames per second. Understanding all these different frame rates and how it relates to what we see on screen is very useful for analyzing videos, because videos often come in different frame rates. Sometimes people record at 30 frames, sometimes at 60, sometimes 25. You've got to take that into account when you're analyzing the physics. Debugging is the video game version of debunking. It's figuring out what's going on. And if you get good at debugging, you can be good at debunking. It just naturally follows. And then coding, finally, if you're a video game coder, you're going to be good at coding. And you can use coding to create simulations. And you can use these simulations to demonstrate things to people about your analysis. You can demonstrate your analysis to other people. So I'm going to go for a few examples of how these things actually apply. But first, the most important idea here, I think, with video games versus UFO analysis is that 3D graphics is video analysis backwards. A video game is a 2D video. When your screen in front of you is just 2 dimensions, it's not 3 dimensions unless you've got some kind of VR headset. And so what appears on the screen is a 2-dimensional video. And to make a 2-dimensional video, you take a 3D world with all these positions in this 3D world. Let me just stop this. Oops. I don't know how to stop it, but so you'll take, for example, like this corner here, this corner here, this corner here. They all exist in a 3D world. This one's further away. This one's closer. The skater itself is closer. You need to take these positions in 3 dimensions and convert them to 2 dimensions. Where are they going to appear on the screen? And this is like the fundamental thing you do in 3D graphics is take 3D and make it 2D. So if you've got something like a UFO video, say this was a video of a flying saucer, It starts out as 2D. But what we want to do is figure out, where is this flying saucer in 3 dimensions? What is it doing in 3 dimensions? Is it moving very, very fast? Is it far away? Is it close to you? So you can take that 2D and take the math that you would have used as a video game programmer that converts 3D into 2D and just flip it. And now you can convert 2 dimensions to 3 dimensions. Or at least you can kind of do that. The problem with converting 2D to 3D is that it's fairly straightforward to go from 3 dimensions to 2 dimensions. We've got these points here, they're in 3 dimensions, and we move them along a line towards the focal point, and where they intersect this canvas, which is the image, that's where they end up. So that's very, very straightforward to go in that direction. And it's fairly easy to reverse the same thing. We can say, like, here's the 2-dimensional points over here, here's the eye, we'll draw a line through it, and we know it's somewhere over here. Problem is, we don't know exactly where it is, because when you go from 3 dimensions to 2 dimensions, you're losing 1 dimension. You're using the depth, how far something is into the screen. You know how far up it is, you know how far across it is, you don't know how far in it is. So you can figure out possible locations for a 3D object, but you can't automatically convert 2D to 3D. It's going to be somewhere along a line of sight from the eye through the 2D point on the screen and out into the 3D world. But once you've got those lines, you can explore the set of possible solutions. Here's an example which might clarify this a little bit. This is a UFO video. This is a video in St. Ives in the UK, Hayle Beach. And you can see a little white dot here, just kind of moving along, and it kind of hovers here for a while. And then in a second, it's going to shoot up into the sky. So we have something comes from here over to here, and it's going to shoot up into the sky. So this is a UFO. And when people look at this the first time, they think, oh my God, it's like this craft that's over on the horizon, because it's just above the horizon. And then it shoots up into the sky at incredible speed. So it must be some kind of amazing flying saucer. The question though is, like, is it actually far away? Is it near or far away? So we can do the analysis I just described on this particular 3D video. There it goes, shooting up into the sky like a rocket. This would be like a rocket if it was several miles away at the horizon. So what we want to do is try to kind of set up a simulation so we can see exactly what might be happening. So I figured out where the camera was, and I'm fitting this field of view to it so I can figure out what it looks like. And then I extract the 2-dimensional positions of the object using motion tracking. This is actually in Adobe After Effects. It figures out exactly where the objects are as it moves along the screen and gives you a whole bunch of 2D positions. And then we can do the deprojection of these positions to convert it to these lines of sight along which the object might actually be. Let me quickly go to the interactive version of this. And this is that setup here. We have the actual video here, and we have a recreation of the video down below, and we can kind of scrub through it here. We can see it move along. So we can see it move in the original video, in the recreation, and in this 3-dimensional version of it. Now, the 3D version is set up at the moment to have the object just over the beach. So we can ask ourselves, is this a physically realistic thing for it to do? And you can see it move around. And up here, I've set up a graph using the 3D physics that we would use in video games to figure out how fast it's going. Turns out it's going very, very slow, less than 10 miles per hour if it's over the beach, which is very consistent with something like a drone. And if we were to take the distance of the object and make it further away, we can see that the speed very rapidly increases into realms that are somewhat implausible for something that's just a hovering object. So we get a range of possibilities based on just adjusting the distance in this 3D model. They all look pretty much the same, but some of them are more realistic than others. So it gives us what might have happened and what is the more plausible explanation. Yes, go on. Oops. So you can see here, I kind of the setup in 3D was very similar to what we had here with this little projection here. We had the same thing here. This is where the camera was, and this is the lines of sight, and these are the possible solutions which we've set up. And we found ones that are physically more realistic, and so that becomes the top of the list. Now, 3D physics, a fundamental part of game programming is this simple 3D physics. And physics in games is basically you store the position of the object, you store its velocity, like how fast it's moving and what direction it's moving. You have various forces acting on the object, including user input. So when you press a button, it makes them jump up. And you basically just add all that together in the proper way and figure out how that object moves. And in Tony Hawk's Pro Skater, that object is a skater. It's 3 dimensions. Use this thing called vector arithmetic, a little bit technical, but very straightforward, really. You use standard equations of motion, which you might remember from school. S equals ut plus half at squared. Anyone? Yeah. You use a thing called Euler integration, which sounds complicated, but it's just basically adding numbers together to get where the skater will be in the next frame, and a bunch of other things. A quick example of 3D physics is the jet in the gimbal video. If we go to that video real quick, let me see, gimbal. All right, so this is a very complicated situation, but I want to focus on one small aspect of it. There's a video down here, famous gimbal video, and it's basically it's filmed from a jet, and we know that the jet is banking to the left, and we can kind of extract these values of the jet and figure out what the bank angle is. And what I did then was do a simulation, a little 3D physics simulation of the jet, and we'll see it kind of reappear right here. Turn the jet on. So here's a little jet flying along with the bank angle matching this particular angle here. And we simulate its position, which then allows us to take other numbers and simulate the lines of sight, and then calculate all these other things and all this radar and these various graphs and all this different analysis. But it's all based on doing a very simple physics calculation, which is essentially implementing a very, very simple flight simulator. But essentially, it's something that you would do as a video game programmer. It's a very typical type of thing to do a simple flight simulator. Pixels example. Pixels, old school video game programmers like myself were very familiar with pixels. And this is the gimbal video. Okay. Same one we just looked at. And I'm zoomed in on one frame, and you see these kind of weird spikes, kind of like ripples. So what's actually going on here? Well, let's actually have a quick look at the pixels. I've got a video viewer here that I can use to zoom in very nicely. So if I zoom in all the way, we can see the pixels are actually just these little squares. And when I go to that particular frame at the end, we can see it's not actually a bunch of curves. It's just a bunch of individual lines that are offset alternatingly. And you might recognize that as being a thing called video interlacing. Back in the day, TV displayed every other line alternating frames. So you would often get these kind of jaggy artifacts between frames. And this is what we're seeing here. We're seeing some video interlacing. But what happened was a scientist with 2 PhDs did a faulty interpretation of that. He took this frame of the video, and he said that what we were seeing were optical interference fringes. Now, the version of the video he took was actually a lot worse than the one I just showed you. It was the one he downloaded off YouTube. So the end result was this kind of strangely smooth curve thing, which he did some analysis on. And he thought that this would allow him to calculate the size and the distance to the UAP, the UFO. Problem was, of course, that what he had here as his input material was nothing at all like the actual image. And so garbage in, garbage out, he did an analysis which was 100% wrong. And this was a person with 2 PhDs. So sometimes, people with PhDs get things wrong. All right, on a slightly less technical note, I don't want to overload you with technical stuff. human factors. We did a lot of focus tests like this one here. You kids don't know what you want. That's why you're still kids, because you're stupid. We did a lot of focus tests with our video games. We'd watch kids and adults play the game, and then we'd ask them about their experience. And we found that a lot of people have trouble describing what their experience was and what they felt about it and what they thought would be an improvement. If you ask someone, how do I improve the game? They'll tell you it's something that generally doesn't make sense. And with UFOs, I've experienced similar things. People are trying to help, but they often tell you things based on what they feel is right rather than what is actually right. So you have to learn to kind of recognize that and get around it. Here's an example. I was sent this video. There's a small version and the zoomed in version by a Korean correspondent. And he said that a witness had seen this weird UFO high up in the sky, way, way up above him. So I asked him to redo it in daytime. And he sent this image, which wasn't from where he took the thing, showing where he thought he was and where he thought he was looking. And then a picture possibly from there showing where he thought the UFO was, just like up there in the sky. So I asked him again to do it. And then he sent me this diagram with Korean notation. I guess that says phone lines and various other things, but not very useful. And then somehow they managed to get the power company to come around and examine the power pole. And they took some other photos. None of those were from the right location, though. So even though I'd asked them very specifically, give me a photo from where you took the photo, they somehow couldn't do it. But I managed to analyze the original video and boost the levels by kind of adding the frames together. And something kind of showed up right there. And we can kind of see roughly where all the power lines and things are. I was able to kind of distort this, even though it wasn't from the right position. And it kind of showed up that it was actually right by the wires. Despite him insisting over and over again that it was nowhere near these wires, turns out it was actually by the wires. And it turns out that what we were looking at was just a little clip on the wire. So, when you're talking to eyewitnesses, they're usually very honest. They're usually trying to help, but they often make mistakes. And this is something that, I've experienced a lot with people trying to describe things in video games. And that experience has been very useful in talking to people politely, because you have to tread carefully when you're kind of saying someone might have made a mistake. Here's a more complicated example. This is the Aguadilla video, a UFO video. It's shot by a Coast Guard in a plane that was circling the Aguadilla airport in Puerto Rico. And it was tracking this weird flying UFO. So here we've got a 2D video. Can we take this 2D video with all these very nice background, little houses and runways and things like that? Can we take this 2D video, convert it into a 3-dimensional world to see what might actually be going on here? Well, this is a great video because it has a lot of data on the screen. We have the camera position in latitude, longitude, and altitude. The camera position is right here. So it says aircraft. And that's the latitude, that's the longitude, and there's the altitude. So that's really, really, really very useful for a reconstruction. We also have the target position. It says over here, target. So it's saying what we're looking at. Now, this isn't actually the object itself. This is what's the ground, what's on the ground behind this crosshairs here. But, also very useful. We have a very detailed background, which we can use to geolocate things more exactly. If something doesn't exactly line up, we can say, like, here's a road. Where is that road? Does it match these coordinates? It's a wonderful video in terms of the amount of data in it. 7,000 frames of data. So what we can do is go through all 7,000 frames of data. We can type in the coordinates from each of the 7,000 frames of data, and that will be a great data set. Luckily, it was already done. Somebody already went through it. They kind of crowdsourced it. A bunch of different people did it. They did it back in 2015. They made a 7,000-line spreadsheet on the Above Top Secret forum. Amazing effort. And it came out to be this wonderfully useful piece of data, which we can use for reconstruction. So we've got these 2 data sets here. One is the planes track, and the other one is the target track. Both of them, of course, are somewhat noisy and low resolution, so we're going to have to do a bit of munging on these. So here, these little white dots represent the actual recorded positions of the plane. Now, planes don't fly in zigzags like this, so we have to use a kind of our general knowledge of physics and how a plane might bank to, again, with our 3D geometry and our munging skills to create a path that smoothly goes through these points. And this gives us a nice camera position, essentially. Next, we've got the target track, which is terrible. It's just this weird squiggly thing. We can't really do very much with it. So what I did there was something you have to do in video game programming, which is create a custom tool to edit the path. And I did that with basically a spline editor. We've got here the original video. We've got my simulation of the video. We see it doesn't quite match. There's the road here, the road down there. Didn't quite match before. So I moved this position of the path. Now it matches. And then keep doing that for the entire thing. And we eventually get a path of lines of sight which matches the what we see in the video. We get a replication. We get a simulation exactly the same. Now we can use that to start analyzing what's going on. So let's have a quick look at that in the interactive way. Aguadilla. So this is software that I wrote. It's also available online. You can run it in a web browser. Again, it's got the actual video up here. It's got the simulated video down here, and it's got all the lines of sight. This line here is the path of the plane. This kind of bluish line down here is the reconstructed lines of sight. And then we can use that, the blue lines are all the lines of sight, and we can figure out a way of going across these lines of sight. And this green line here ends up being the very simplest way you can traverse the lines of sight. And it turns out that if you start here and you go to here, starting about 18 miles per hour, kind of descending gradually, you get a trajectory which solves this problem perfectly. Now, of course, there are other solutions. There is this red one down here. This will be something that is moving down by the surface and not actually moving high in the sky. Like this green one is actually fairly high up above the runway. And the red one is low down to the ground, and it actually goes underwater at various points over here. So we have to ask ourselves, like, which one of these two is more likely? We've come up with some solutions. One is physically very plausible. The other one kind of maybe looks more exciting, but is it actually something that's plausible? So with that, we end up having two possible solutions, and then we have to kind of do our analysis of those and perhaps do a bit of human factors. Why does this super fast thing whizzing over the ground look more enticing to people? Well, it looks more enticing because that's what the video actually looks like. The video looks like something whizzing over the ground. But is this 18 mile per hour version plausible? Well, it turns out that just upwind of this location, there is a hotel about here, just off the map here, where they release wedding lanterns, these so-called Chinese lanterns or sky lanterns or fire lanterns. They're just kind of big paper bags, and they've got like a little bit of burning fuel in the bottom, and they will release them here. Normally they will go out to sea, but the wind that day was blowing over the ocean, over the airport. So it seems quite likely that a couple of very low speed sky lanterns were just drifting over the ocean, and this plane was just flying around them and making it look like they were zipping over the ground in some kind of weird way and going underwater and doing all kinds of weird, physically implausible things. So we end up with two hypotheses, one of which is more physically plausible, but the only way we got there was by doing a lot of programming, a lot of analysis, and a lot of things that were based very much on my game programming experience. So, in summary, video game programmers, it turns out, are actually well suited to UFO analysis. People with PhDs sometimes get things wrong. We all have different knowledge domains. I know a lot about 3D graphics. I know a lot about pixels. I know a lot about basic physics. And someone with a PhD in physics will know a lot more about, say, I don't know, quarks and muons and electron levels and things like that. And, they probably will know the basics too as well. But, their area of expertise is perhaps not always appropriate for analyzing simple UFO videos, where basic physics actually is more useful. The problem, of course, is that people are going to dismiss analysis that they don't like, no matter where it's from. It would be great if we could get all the UFO believers to watch this video. They'll see it and be like, oh, yeah, great. Mick's really good at coding, and he's really good at analyzing UFO videos, but he's maybe even better than this guy with the PhDs. But I prefer the other explanation. If there are two good explanations and one of them is something that they like better, they're just going to go with that one. So really, it's about how well you analyze the data and how well you present that data in an understandable manner. You've got to do a accessible presentation of the data. You can't just say, I'm an expert. I can't just say, I'm a highly qualified video game programmer or a highly qualified guy with 2 PhDs, and I think that it is this. You've got to do a compelling looking and accurate and honest analysis and a presentation of that data. And that's something where video coding experience and an understanding of human factors can be very useful. It is very useful to in both the analysis stage and in the presentation phase. And this is something that I've really enjoyed doing, and I'm going to continue doing, I think, for the foreseeable future. And hopefully I will convert a few more people.